Today we discuss about specific heat of a gas, specific heat of a material, specific heat of a material that is defined by this. It is the quantity of heat required to raise the temperature of unit mass of the material through 1 degree. Okay. It is the quantity of heat required to raise the temperature of unit mass of the material through 1 degree. So, suppose for a material you are supplying heat Q amount of heat is applied to it, and suppose its mass is m, and you raise its temperature by delta T, then this will be Q by m delta T. That is the quantity of heat required to raise the temperature unit mass. We are dividing this by m, so unit mass of the material through 1 degree. Okay, so this is the specific heat. So this definition is actually sufficient for solids and liquids. Okay, sufficient for solids and liquids, but for gases actually there has to be something more we have to define. Actually, we can supply heat to a gas at a constant pressure and at a constant volume. Okay, so a gas can absorb heat, its temperature can increase by at a constant pressure and constant volume. So we have two kinds of specific heats. Two types of specific heats. One is specific heat at a constant pressure, which is Cp equal to delta Q or delta T or dou Q dou T at a constant pressure. Okay, dou Q dou T at a constant pressure. It is the amount of heat required to raise temperature of unit mass of the gas through 1 Kelvin at a constant pressure. So the amount of heat required to raise the temperature of unit mass of the gas through 1 Kelvin at a constant pressure. So this is Cp, okay, dou Q dou T at a constant pressure. And volume Cv, specific heat at a constant volume Cv, that is dou Q dou T, delta Q dou T at a constant volume, dou Q dou T at a constant volume. Okay. So this is the amount of heat required to raise temperature of unit mass of the gas through 1 Kelvin at a constant volume, the same thing, at a constant volume. And it is defined dou Q dou T at a constant volume. So we have Cp and the Cv for gases. Okay. Now Cp is always greater than Cv. Cp, the specific heat at a constant pressure, is always greater than specific heat at a constant volume, because when you supply heat to a gas and allow it to expand at a constant pressure, the heat supplied, the heat energy supplied, that is used for two purposes: to increase internal energy, and in that way the temperature increases, and to do work in expanding the gas against external pressure. Okay, so we have a kind of gas taken in a vessel, and this is the piston. This is a piston, and when you supply heat, external heat is supplied. What happens is a part of it is used for increasing the internal energy, and as internal energy increases, the temperature increases. And as the piston moves, the gas does work. Okay, because the gas has to be at a constant pressure. To maintain at the constant pressure, the piston has to move. So it does work against the external pressure. So we have delta Q, the heat supplied for increasing internal energy and for doing work, PdV. Now if it is at a constant volume, okay, This is at a constant pressure. So at constant pressure the volume changes as the piston moves. So this is the heat supplied dq delta q equal to du plus pdv. But in the case of gas heated at a constant volume, suppose you fix the piston is fixed, that means the volume is fixed. So dv 0, so pdv 0. So when the heat supplied is used to increase its temperature. Okay, the whole heat is applied is used to raise its temperature, so increasing its internal energy. Okay, so for the same change in temperature, if you heat the gas at constant pressure and constant volume, the constant pressure situation requires more energy, more heat to be supplied. Okay, so more heat is required for increasing the temperature of gas through 1 Kelvin at a constant pressure than at a constant volume, because at constant pressure the gas has to do work as well. Okay, so Cp is always greater than Cv. Heat supplied will be more and Cp is greater than Cv. And in the case of perfect gas, we will see Cp minus Cv, that is given by R, the gas constant. Now let's obtain the relation between Cp and Cv. Okay, relation between Cp and Cv. Internal energy is a single valued function of pressure, the thermodynamic variables, pressure, volume, temperature, etc. But for a gas, any two variables are sufficient. Okay, because if you fix two variables, other variables are fixed because of the relations connecting these variables. So we are choosing volume and temperature as the independent variables. So U is a function of volume and temperature. We are choosing these two variables as independent variables. Okay, we have the freedom. Now U, internal energy, that's a function of volume and temperature. Du U is a perfect differential. So du, that is dou U dou T dt, dou U dou V dV. Okay, and delta Q, that is given by du plus delta W. The only thing here we are using delta is because it is not a perfect differential like U. Okay, actually the meaning is same. You supply some amount of heat, delta Q, and this is du is the increase in energy, internal energy, and delta W is the small amount of work done. And delta Q now, that is equal to du plus pdv. Okay, du plus pdv, because delta W, that is the work done, that is pdv. If it is at a constant volume, this will be 0, pdv will be 0. Okay, constant volume, this will be 0. But we are taking a general case, so we assume there is a change in the volume. Anyway, delta Q, that is now if you substitute for du, we have dou U dou T constant volume dt, dou U dou V constant volume temperature T, dV pdv. So delta Q by delta T, that will be dou U dou T at constant volume, dou U dou V at constant temperature, dV by dt plus pdv by dt. And this is given by dou U dou T at constant volume. Then we are taking this as a common factor. So this is P plus dV by dt, dou U dou V at a constant T. And if you are considering this at constant volume, we have Cv. And constant volume, this dV is 0. This is 0, dou V by dou T or dou V dV by dt, that is equal to, this dV by dt is 0. Okay, this is 0, dV by dt, that is equal to, there is no change in the volume. Okay, so this factor is 0. So we have Cv as equal to dou q dou t, that is dou u dou t at a constant volume. Okay, so the one important point is dou q dou t at a constant volume, that is equal to dou u dou t at a constant volume. These two are same. Okay, dou q dou t at a constant volume, that is dou u dou t at a constant volume, because now when gas is heated at a constant pressure, when gas is heated at a constant pressure, we have dou q dou t at a constant pressure, that is Cp. So dou q dou t at a constant pressure, that is given by dou u dou t at a constant volume, plus P plus dou u dou v at a constant temperature, dou v dou t at a constant pressure. Okay. So what is it? This is Cp, and this we know, dou u dou t at a constant volume, that is equal to dou q dou t at a constant volume. So this is Cv, then P plus dou u dou t, dou u dou v t, then dou v dou t at a constant pressure. Now for an ideal gas, if you are considering an ideal gas, this U, the internal energy, is a function of temperature only. For an ideal gas, generally U is a function of two variables. Okay, but for an ideal gas, it does not depend on volume, how close the molecules are, or how far apart the molecules are. It does not depend on that. So the internal energy is a function of temperature only. So dou u by dou v at a constant, dou u by dou v. Okay, dou u by dou v, this is equal to 0. So we have Cp equal to Cv plus P dou u by dou t at a constant pressure. For an ideal gas, Pv, we know that is equal to RT. So as we take P dou v dou t, that will be equal to R. So this is P dou v by dou t at a constant pressure, this is equal to R. So Cp minus Cv, that is equal to R. Okay, Cp minus Cv, because P dou u dou t at a constant pressure is R, Cp minus Cv, that is equal to R. So, and this is the Mayer's relation. Okay, the Mayer's relation, Cp minus Cv equal to R, only for ideal gas. But generally Cp is always greater than Cv. Okay, Cp is always greater than Cv. Now let's obtain a adiabatic equation of a perfect gas. A perfect gas is expanding adiabatically, and we want to obtain the equation. We consider 1 mole of a perfect gas insulated from the surroundings, and the first law, delta Q equal to du plus delta W, this is P dV. So delta Q is du plus P dV, and in the case of an adiabatic process, we know the system will be completely isolated from the surroundings. Okay, this will be perfectly isolated from the surroundings. Okay, this is perfectly isolated from the surroundings. So delta Q is equal to 0. So we have du plus P dV, and we know Cv. The Cv is dou u dou t or du dt. You can write because we are considering a kind of perfect gas where U is function of temperature only. Okay, so du is Cv dt, so that we substitute P dV, and Pv is RT. Okay, and as we take the differential, P dV plus V dP, that is equal to R dt. So for dt, I can get what? P dV plus V dP by R. So this is dt. So this dt I am substituting P dV plus V dP by R and plus P dV. And for this R, I am substituting Cp minus Cv. Okay, here I am substituting Cp minus Cv. So this is Cv PdV plus Vdp, and here Cp minus Cv dV. So this is Cv PdV plus Cv Vdp. Here we have Cp minus Cv PdV. Okay, and we have Cv Vdp plus Cp PdV. Okay, Cv Vdp plus these terms get cancelled. So we divide the throughout by PVCV. We are dividing throughout by PVCV. So we have dP by P 0 equal to dP by P or Cp by Cv dV by V. Then 0 equal to dP by P plus Cp by Cv dV by V. As we take Cp by Cv as gamma, and as we integrate the log P, that is gamma plus log V, that is a constant. So log P plus log V to the power gamma constant, log PV to PV to the power gamma constant, and PV to the power gamma a constant. So we get the equation for adiabatic process. Pressure volume to the power gamma, that is a constant. This is for the ideal gas only. For isothermal process, we know PV is a constant. Okay, that we know for adiabatic process, P V to the power gamma, that is a constant. Now the different form of these equations are there. We just we take PV to the power gamma constant. We know PV equal to RT for 1 mole, V equal to RT by P. So that we substitute V equal to RT by P, we substitute, and we have T to the power gamma, P to the power gamma minus 1 constant, or P to the power gamma minus 1, T to the power gamma, that is a constant. Also P equal to RT by V, and for pressure we are substituting RT by V. Then we get T V to the power gamma minus 1, a constant. Okay. Here we have V to the power gamma V, so T V to the power gamma minus 1, that is a constant. So these are the different forms of the adiabatic equation.